Hello and welcome to our final video for Unit 1. In this video, we're going to be talking about a technique for solving for a single variable called Cramer's rule. But to help us get there, we're going to begin with a little bit of a review of some stuff that we did earlier this week, just to kind of remind ourselves of this process. So note 11 says, suppose I have a system of linear equations that's given by ax equals b. And we saw earlier, if A has an inverse, then we can multiply both sides of this equation by the inverse. So A inverse times AX is equal to A inverse times B if A inverse exists. And then through the associative property, we can regroup here, and we get A inverse A times X is equal to A inverse B. But A inverse times A is the identity, so we get an identity matrix times X is equal to A inverse B. But because of the lemma we started this week off with, the identity times anything is the identity. So we can just solve this system in this manner. So let's do an example of applying this technique, just again to refresh our minds on how this would work. For this example, we're going to make use of an inverse we found earlier in example 53. So in example 53, we had this matrix A, and we found this to be its inverse. All those delightful fractions, remember? So we're going to be using this inverse because the coefficient matrix of this system of equations is the same as matrix A. Let's just do a quick check. For the rows, we had 3, -1, 0, 3, -1, 0. Yay. 0, 2, -1, 0, 2, -1. Yay. And then -8, 2, 1, -8, 2, and 1. Hooray. So if I want to use A inverse to solve this system, all I have to do, according to our work here, is take in A inverse times the constant matrix B. So we're going to take that A inverse and multiply it by this column matrix. So we'll take 1, 2, 4, 1/4, 3/4, 1/2, 1/4, 3/4, 3/2, and we'll multiply it by 3, 5, -13. So let's walk through this. Let's see, I'm going to be involving quarters for this first one, so I'm going to think in terms of quarters. So for instance, 1 times 3 is 3, but that's going to be 12 quarters. So I'm going to have 12 plus 5 minus 13 should give me 4 quarters, which is 1. Then again, I have quarters here, so I'm also going to think in quarters now. So 2 times 3 is 6, but that's 24 quarters. So I have 24, let me write this down here, plus 15 minus 39 quarters. That's how I'm thinking of these problems. So let's see, 24 plus 15 is 39. Oh, and 39 minus 39 is 0. So we don't have to worry about that too much. And then for this third row, our fractions are in terms of halves, so I'm going to think in terms of halves. So 4 times 3 is 12, which is 24 halves, plus 5 minus 39. So 24 plus 5 is 29. Minus 39 gives me a -10 over 2, which is -5. So there we go. This is going to be our solution to the system. If we wanted to check it, we can do so. So let's plug in 1 for x1, 0 for x2, and -5 for x3 and see if we did this correctly. So we get 3 minus 0 is 3. 2 times 0 minus -5 is 5. And now we have -8 plus 0 minus 5 is -13. So it works. Okay, so now that we've kind of refreshed our brains and put this back into our memories, we're going to continue note 11 into note 12. So I'm just going to leave note 11 here so we have it as reference. So let's continue the fun in note 12. So what I'm going to do is I'm going to write this in terms of the adjoint. Remember, we had a formula for A inverse as 1 over the determinant times the adjoint of A. So X is going to equal 1 over the determinant of A times the adjoint of A times B. Now be careful when you're using this notation to remember what's a scalar and what's a matrix. The determinant's a scalar, the adjoint's a matrix, right? So you want to keep, even though they kind of look like they're similar objects, they're definitely not. Now, instead of thinking of this full matrix, I'm just going to pluck out one X sub I in particular. So I'm going to say this is going to imply that if you give me an arbitrary ith value of X, that's going to give me 1 over the determinant of A times the sum over K of the adjoint of A, IK, B, KJ. Now, because B is a column matrix, there's only one column. So you can think of J as just a 1, or very often we'll just write it with a single subscript referring to each of those rows. So this is sort of typical notation that we're going to have. Now, remember that the adjoint of A is made up of the cofactor elements. So essentially what we have here is we're adding together a bunch of cofactors times a bunch of scalar values. This is what happens when we find the determinant. When we find the determinant, say along a row, you take the value in that row times the cofactor plus the value in the next row or next column, right, times the cofactor and so on and so forth. So that's what we're doing here. We've got a bunch of cofactors here being multiplied by these scalar values from B. So what this amounts to the determinant of A with the ith column replaced with B. Now, you might be wondering, okay, why? Why do we care? So the reason we care is because if I want to find just one value for X, I don't have to solve the whole system. I don't even have to find A inverse now. All I have to do is find the determinant of my matrix A, and then I replace whatever column I'm interested in. So if this is X4, I replace the 4th column with B and find the determinant of that matrix. And then I find their quotient, essentially. So that's all we have to do for an individual value. And of course, we could solve the system this way by doing this process for all of the entries. So because this is a new thing and we want to practice with new things, let's do an example of doing that. So this process, I'm going to define it first formally, is known as Cramer's rule. And then we'll apply Cramer's rule to solving a system of equations. All right, folks, here we go. This is definition 22. Cramer's rule. So we're going to suppose that A is an n by n invertible matrix. And X, B, well, X and B are n by 1 matrices. Then little x sub I is equal to the determinant of capital AI over the determinant of A, where AI is the matrix A, with the ith column replaced with B. So this is essentially just summarizing what we saw in notes 11 and 12. So in order to find the value for one particular variable, we can find the determinant of A and the determinant of A with the ith column replaced by matrix B. So let's do an example of seeing Cramer's rule in use. So for example 56, we're going to use Cramer's rule to solve this system of equations. And just as a reminder to myself and you, I've written down what Cramer's rule formula piece was. So we're going to find the determinant of A and the determinant of AI. Now, because we were told to solve, we're going to have to use Cramer's rule to find X, and then we'll use it again to find Y, and then we'll use it one more time to find Z. So sometimes you might be asked to use Cramer's rule to solve a whole system, and other times you might just be told solve for Y with Cramer's rule. So make sure you read the directions carefully because you don't want to do more work or less work than what you're being asked to do, right? So to begin with, we need to state A and B, and we're going to need the determinant of A. So that's where I like to start with Cramer's rule. A is our coefficient matrix. So A is 5, -1, 3, 2, -1, 1, 1, -5, and 2. And B is just this matrix, this column vector here. So we have 0, -9, and 0. Now we have to find the determinant of A. So lots of different ways, right? So we could use some row reduction, we can use the definition, however you want to find the determinant. I'm going to speed along through it. I think I'm going to use row 2 here, just because 2 and 1 look like nice numbers to be multiplying by. So you find the determinant, I find the determinant, and then we'll check and see if we get the same thing, all right? All right, welcome back. Did you find the determinant? So when I expand it along the second row here was my work, if you want to take a moment to look at it, and I ended up with -9 in the end. So what was a bit of a bummer using the definition here is that none of the entries in A are 0. So it just was a pain to find. But the good news is when we go to find the determinants of the A sub i's, we're going to be replacing the ith column with B. And B has 2 zeros. So that's going to enable us to find the determinant along that new column. And we'll really only have to focus on this -9 piece. So I've rewritten my determinant over here so I can erase this and make some space. Let's do one of these together, and then I'll leave the other 2 for you to practice on. So let's remove this piece here. And we're going to find X. Now you can think of X as X1, Y as X2, and Z as X3, right? So if you want to think of it in terms of that context, so you know where the i's are. So X is the same as X1, which means we're going to replace this first column with this one here and find the determinant. So I'm replacing this first column with 0, -9, 0. And then the other 2 are the same. For my formula, X sub I is going to equal that over the determinant of A. So the determinant of A was -9. So I'm going to multiply this by -1/9 for this problem. So again, as I mentioned, I'm going to expand along this first column here because of those zeros. So this is going to give me, bringing this -1/9, bringing the -1/9 down. And then let's do this determinant in a different color just to keep it separate. So 0 times whatever, we don't care. -9 times -1 to the 2 + 1 power. Get rid of the second row in the first column. And that will give us -2 + 15. And then we have plus 0 times whatever, we don't care. So this is going to give us negative 1/9 times negative 9 times negative 1, because we have an odd power, times 13. What's nice is these two values cancel on us, and we end up with negative 13. So if I'm writing down my solution, x, y, z, we now know that x is going to be negative 13. So you are going to repeat this process, but now, instead of replacing the first column of A with B, you're going to leave that one alone and replace this second column with B, and repeat this process. That will tell you why. And then we're going to keep the first two columns and replace the third one with B, and that's going to tell you Z. So take a moment, pause the video, work through it, unpause, and then my work will be on the board so we can check. Okay, let's see how we did. So for my y value, I have x2, and that's going to be negative 1/9, because it's the reciprocal of the determinant, times the determinant of keeping the first and the third columns. Now the second is replaced by 0, 9, 0. I'm noticing on my screen this looks kind of fuzzy, so I do apologize if you can't read the green. This says negative 1/9 times negative 9 times negative 1 to the 4th times 10 minus 3. Those are the determinant values I found. And then 10 minus 3 gave me 7. And then when I multiplied it all out, I ended up with just 7 in the end. For Z, that was x3, so I did the same process, except now I replaced column 3 with 0, negative 9, 0, worked through it, and ended up with a positive 24 in the end. Okay, so that does it not only for this video, not only for this week, but for our whole first unit. So unit 1 is done, y'all. I can't believe it. Next week, we'll be starting our next unit, unit 2. And unit 2 is going to have kind of a similar flavor to it as one of the examples we did at the end of our last video. So at the end of the last video, do you remember we had a 3x3 matrix and it had like e to the t in it with like sine t and cos t? So that was a matrix that defined a function moving from the set of all real numbers to the set of 3x3 matrices. So you might be wondering, okay, but we haven't had functions like that before. We've maybe moved from all real numbers to all real numbers, but now we're moving between two different spaces. So it turns out that those spaces that we want to move between with functions has to be pretty well defined. And we're only going to look at one particular type of space, namely a vector space. So our next unit is an introduction to vector spaces from a linear algebra point of view. You may have seen vectors before in terms of like n tuples before. Now we're going to see them in terms of matrices. And in fact, our vector spaces are really just spaces that satisfy a set of conditions. And so anything can be a vector. It doesn't even have to be a column vector or a row vector. Like this 3x3 matrix could be considered a vector if our vector space is the set of all 3x3 matrices. So you might want to let go a little bit of what your idea of a vector is. We're still going to keep some of those concepts, but we're going to think more broadly than just to vectors in Rn. So that's where we're headed. Yeah, so looking forward to seeing you with vector spaces. But in the meantime, I hope that you found this video about Cramer's rule helpful. And until next time, happy mathing. Bye.